Well, good morning, everyone. Hola, guapos. ¿Cómo tal? Huh? It's my pleasure to be here, and I would like to really thank also everybody, including Rainer, for this opportunity to be here and really having a fantastic view on the one side, but also having this nice public here. And it's my job now to wake you guys up, right? Scientifically wake up, concerning really that we want to all go for something that is really connecting us, which is this kind of very tiny, tiny cantilever, as you see here, right? So this is basically the starting point of all these actions that we are going here, and I'm happy to see that also Dorota and everybody has made up this kind of larger project. So what qualifies me actually to talk about scanning force microscopy or AFM in general? And the reason is basically, okay, I had the chance really 35 years back to already start working together with Binnig and Rohrer and Christoph Gerber and these people in Switzerland. I'm Swiss, from top to the bottom. And this means actually I could really learn from them how to operate such a system. And today we just take such a cantilever and we just push buttons, right? And we believe that what we see is exactly our near field or our nanophotonics polaritons that we want to measure. And so when Rainer asked me and Andreas Beck actually to really give an introduction, what can we do wrong with AFM? Then I said, okay, I'm happy to really actually get you on the same track. So I'm from Dresden, so to say. I moved, as you see, from Switzerland down here somewhere into Dresden. And that's a nice connection to what just Dorota was telling you, semiconductor industry. And when you guys hear semiconductor, you always think about the Silicon Valley, right? Now, Dresden, by the way, is the Silicon Valley of Europe. And Infineon just bought up, they're just building a new manufacturing with 5,000 employees, new jobs for you guys, possibly also in near-field optics, and they do near-field optics, in fact. So Dresden is one place, actually, that, where we do a lot of stuff, and we had the chance to really join into the excellence of the initiative. So we're coming back to excellence here. And in our job, actually, we want to use this kind of small gadget, this kind of cantilever, to use that for electronics on the one side, for magnetism, for photonics, and you can see it basically here. So it's the in and out, it's our sensing device with which we want to really do that job. And in fact, to give you just a small glimpse of what we can do with that, is a list of things that I try to cover within this lecture, not this one here, but also the second one. I want to get you back that this scanning force microscope, I'm calling it not atomic force microscope, and you will see in the reason why this scanning force microscope has so many options to measure topography on the one side, to go for magnetism, to measure electrostatics or time-dependent electrostatics, to make dissipation on the system, because you're hitting with your cantilever on your surfaces, and on top of that, also combine that with SNOM. So you see there are many, many different things at the same time happening. Well, to get you back on the same page, we are doing also near-field optics, and we just have two such spec systems. Our specialty is to couple that system in the terahertz range to large facilities lasers, which is a free electron laser. This is about 20 meters long, and also a super radiant source, which gives us the opportunity to go down to wavelengths of 3 millimeter. This is 100 gigahertz. So if you're interested in doing such research with us, then this is a user facility, and you can apply for basically beam time. So this is really the upper end of the story. But we want to start now very simple. We want to start at the beginning, which is exactly this scanning force tip. So we need to understand what is it really doing. So we take this cantilever back, and we see actually there's a tip. We now want to see a little bit about history. We want to talk about the cantilever properties, because that's essential, because what you measure here, you see, you can go even dynamic. And it's very important that you stay dynamic on that. We want to see about cantilever deflection opportunities, the forces that are relevant, and finally also different operation modes. Okay, let's start, and we go back 1986. That's the starting point of everything here, because in 1986, three things happened at the same time. Okay, a little bit delayed. The first thing to mention here is, again, this one here, Santiago de Compostela, not too far off, about 600 kilometers to the west here. You can walk it, actually, and it's a very nice walk on the Jacobs Way. Santiago de Compostela was the very first place in 1986 in July where Nico Garcia from the Universidad Autónoma de Madrid was organizing the very first conference on scanning tunneling microscopy. I don't know who was knowing that. Maybe you know. Well, no. Okay. So this was the very first starting point where the community of STM was growing. And in fact, this is actually the first point in 1986. Second point, a little bit later, the same guys, Heini Rohrer, Gerd Binnig, were receiving the Nobel Prize. This is October, as you guys know. Nobel Prizes are always actually contributed or distributed actually in October 1986, and they got the Nobel Prize together with Ernst Ruska for electron microscopy. So it's half-half, as you see, one quarter, one half. But what is important is that not Heini Rohrer, not Gerd Binnig were really doing the job, but that guy on the right side, which is Christoph Gerber, was the guy in the lab doing all the measurements. And this is Christoph Gerber. He was never at the, let's say, awarding actually of the Nobel Prize, but he went the same year together with Gerd Binnig. He went to California to Carl Quaid's laboratory, Ginsten laboratory, which is torn down at the moment, so you can't really visit anymore. And they said, okay, let's develop something which is called atomic force microscope or scanning force microscope, published exactly in this kind of PRL in 1986, because they said, okay, we are a little bit bored of our STM, because our STM is very nice, because our STM can really measure currents through an XYZ scanning of this piezo, but that's electrostatics, tunneling measurements, and so on. What about insulators? Can we also do the same thing when we go for insulating surfaces? And the answer is, they developed exactly this kind of cartoon. It's a lever where you have a tip attached that is sensitive to any kind of forces. And they said, okay, simply we need a sensor. This is actually from Gerd Binnig, a slide he was really presenting at the Nobel Prize talk. So that was exactly the starting point. The scanning force, this kind of gadget, basically was developed exactly in 1986. And you see in the first publication, 1986, they said, okay, let's take such a cantilever. Here you see schematically. And you put it on a sample, which is on the left side. You have a scanner for the sample, which is called a feedback here on AFM. And on the right side, they said, okay, we need a mimic to measure this. Okay, they didn't have anything ready, so they said, okay, why don't you take an STM? So make a tandem. And in fact, that's why actually they came up with the idea to measure atomic forces. And that's exactly the point where the branding name AFM, atomic forces, was delivered. Well, it caused a couple of confusion because some people thought in communities AFM is atomic force. You're going for nuclear physics, and it's not. It's solid state physics. I rather like to really name it scanning force because we're measuring generally forces in total. Atomic force is one type of forces, and you will see in a second there's more. So let's turn page. We need to know a little bit actually on this cantilever. Before we can really start doing measurements, we need to know what are the static and what are the dynamic properties of this cantilever. And you see, first of all, we take such kind of a cantilever. Well, here it's a very nice silicon-based cantilever. In the early days, I can tell you what we did. We went into the kitchen. You know, there's aluminum foil that you wrap up your sandwich in. You took a scissors and you cut actually cantilevers out of aluminum foil. Very tiny, tiny ones. It was working, okay, not so splendid, but it was really actually a good approach. Now we take this cantilever, and you see nicely, basically, you have a certain deflection of this cantilever. Let's call this Z0. That's exactly my deflection. And this is so tiny that we can apply Hooke's law, which means that the force is really linear on Z0. We don't have to go for nonlinear developments of these forces. And even more, if you take a feedback that keeps actually the deflection constant, you're better off actually with this Hooke's law. So that means the cantilever force constant, the spring constant K, is exactly what you have here. Now, if you go for math, you see, okay, well, this spring constant is something that is related to the material constant, the Young's modulus, as well as the geometry, length times width, and so on. And moreover, the length, you see, L power 3. So the longer the cantilever, the smaller the spring constant. If I go short, ping, okay, you see basically I get a much, much stronger. This goes with power 3 law. Now, the moment of inertia, E, is important because that's a cross-section. You can quasi-calculate that if it's really square like you see here. Then you go basically for width times thickness power 3, and you get exactly this, which ends up in my force depending on the deflection Z0 exactly in this manner. So this is the static point. We keep the cantilever like this. You basically stay there. You go into your sample possibly, and you stay. Wonderful. Now let's go dynamic because that's much more important in life.
you want to be dynamic. Well, everybody knows here harmonic oscillator, which means if you take a pendulum, right, you guys know what the solution to this kind of dynamic property is, because it's a harmonic oscillator which has eigenstates that are spaced equally, which means we go up exactly by h bar omega, always. Ground state, first order state, second order, and so on. This is just quantum physics, right? And this is basically simply because we have a harmonic oscillator where we have a mass, a concentrated mass at the end, and we say, well, my spring here basically, or my rope has no mass at all. So what about actually if we go really for this kind of cantilever now? We have two options how we can calculate that. One thing is actually we could say exactly the same way like we go for energy. Potential energy basically is the same like the dynamic energy, which means we have a deformation, okay, which means this is a deformation energy which is exactly proportional to my deflection z0. Or, and I have the dynamic one, which is basically the velocity. Or in other words, it's the frequency omega 0 that comes in, the eigenfrequency, which is the lowest eigenstate of the system. You equate these two things, balance off forces or energies, which means my eigenresonance frequency is simply a geometry factor, again, EI, times A and rho. A is the cross-section W times T. You see that basically here. And rho, the density of the material. The beta is a so-called normalized constant, and you see nicely it's a factor of 1.8788. Keep this in mind. I will ask you later, okay? 1.8788, okay. So this is one way to approach by energy, and that's exactly the poor man's version, because we miss half of the world, or even more than that. What we should do rather is actually we should really go and really solve the equation of motion of this cantilever. So we go dynamic, we have a dynamic oscillation. And you see nicely that if you go and do the math right, we have this kind of equation to solve. You say, well, it's a harmonic oscillation. But what we're doing is actually we say already that we want to have higher order excitation modes. Not only the fundamental one, but also higher orders. See, n is an index number going from 0, 1, 2, 3, and so on. So similar like my ground state, we have a 0, first, second, third excited state. So it's really quantum physics that we do here. So if you plug this in, basically your solution, or let's say your equation comes up actually in a fourth order differential equation that we have to solve with some kind of normalized frequencies again. And we can now make an approximation. That means we take any solution that is possible. So you see basically it's a harmonic oscillation, so why not to take sine and cosine waves? We don't know what is really the right one. They're just phase shifted 90 degrees. But on the other side, you see also, if I'm going to excite it, it's going to have a damping, right? So there's basically a damping of the system, which means we take sine hyperbolic and cosine hyperbolic at the same time. Which means we get 4 solutions here. We need 4 boundary conditions, which is clamping my hand, which means first order, second order is really 0. And the open end also has the third and the fourth order to be 0, which means in the end, we get 4 solutions, which ends up in this solution of my cantilever oscillation. That's what we want to see. And this gives us solutions, which is not only one solution, but we see nicely, they're higher orders. The first one is actually 1.875. So remember, how much was the beta before? Exactly, fantastic. So very close to that value, but nevertheless, we see higher orders. So if you plug in 4.694, this solution is also fulfilled. We can go for 7.8. So in fact, you see we get higher orders for this solution. This is fundamental mode, omega 0, first order, second order, third order, and so on. And they're not equidistant. So it's not 0, 1, 2, 3, 4. It's not h bar omega, it's more. How much? Well, let's see. So we do that. We calculate exactly omega n, and we go for denormalized omega n over omega 0. Omega 0 means the fundamental resonance frequency, basically about 2 hertz here. And that means the higher order mode obviously must be 6 times, 3 times larger. So let's try to excite this. Ooh, maybe you can see it now, huh? You see there's a node here, okay? If I go for 12 hertz, 12.56 hertz, I have a node there, which means that my solutions now are higher order modes. We get the fundamental mode here, we get the first order mode here, we get the second order mode, and so on. So your cantilever has more than one mode to go. So if you go dynamic, you can excite any of these modes in your cantilever. It's not at 2 omega 0, but it's at 6.3 times omega 0. The third order is at 70.5 omega 0, okay? And so on. So that means if you buy a lock-in, look that it has enough bandwidth, okay? So we see, the comparison between energy conservation and equation of motion is quite close for the fundamental mode. And in fact, if you plug this all together, we can find, that my omega 0, which is now exactly the K0 or the kappa 0, this is the full formula, goes exactly to K over M lever times 0.24 in the denomination here. Well, that means my effective omega 0 is about twice as large as K over M. So it's much larger than a free oscillator that we had, my pendulum before, K over M, right? It's a factor of 2 off. Question for you, why? Why is that? If you take the same mass at the front end of my pendulum, and I take the same cantilever mass, why do we have a different, so to say, oscillation frequency? Question to you, why? Well, the difference is clear. Here we have a distributed mass. The mass is not at the front end. It's not a concentrated mass, but it's really distributed, which means, in average, half of it basically is not really contributing. So just hand-waving argument, you can really see, you go for a concrete calculation, which is this one here, it's just a factor of 2. If you add some concentrated mass in the front, because of my tip here, then I'm just adding this one here to the front. Jesus. I'm just adding this to the front end, and you see nicely that we can really calculate the effective resonance frequency. So when you calculate, or when you measure your resonance frequency, be aware that this is all in it. So the concentrated mass plus that actually lever mass weighted has to be respected, and then only you can really calculate your force constant, your spring constant of your cantilever. Here's a table, basically, of all the things that we need to know. Only 2 things need to be known. Actually, the geometry, that's clear, but also the Young's modulus on the one side. If you take silicon, it's 1.79. If you take rho, the density, it's a 2.3. Fine. Okay, this is all clear. And we can turn page and say, okay, now let's go and try to measure this cantilever deflection. And I would like to really briefly strive historically whatever has been proposed to that, which are electrical measurements on the one side, here on the left side, using an STM on the back side, capacitive or piezo resistive. And on the right side are the ones, more modern type, which are optical measurement. You see beam deflection, which is the most known one to you guys. You adjust your knobs, the 4 knobs, in order to get the beam deflection right. But there are better ones concerning sensitivity, right? Homodyne and heterodyne interferometry, and also one very, very special technique called differential polarization. Well, let's see how we go in time, and we were going to really strive that. Historically said, Binnig, Gerber, and Quaid said, well, let's take this cantilever and put the S10 behind. Well, this means we need to really collect the tunneling current. You see the tunneling current here, the density, is proportional to my exponential value with phi, the distance between the tip and my cantilever. Well, is this good? Is this bad? Well, I have this picture here for you. This is a real picture how your STM tip looks on the backside of your cantilever. And you see how dramatically impacting it is. So we have some pros. It's a very accurate measurement with your STM tip, and it's very historical. But there are tons of cons, actually, as you see. You need a backside that is really conductive on the one side. It has a certain roughness, because you're evaporating gold or so on the backside, which means the surface topography of that one matters. Then you need stronger forces, because that's an electrostatic interaction, finally. You get adhesion of your tip and so on. The feedback loop is twice for the STM and for the AFM. And then we have a very low bandwidth, typically below 1 kilohertz, which is really low. And hence, it's not very suited for dynamics. Remember these kind of dynamic modes, higher orders, you can forget about that. So no way. So that's why it was abandoned. People thought, well, let's go dynamic and let's go for a capacitive sensing. And this is actually at ZSEM. They have done this, so to say, in Switzerland, with Jürgen Brucker and others, and Jim Jimczewski, saying, okay, why not to take a capacitor from the backside of my cantilever in order to detune, as you nicely see here, my capacitance when I'm vibrating the cantilever. So you have an oscillation, you're an LC circuit, as you see nicely, and you have a certain frequency, and you detune that by simply vibrating your cantilever. What is needed for that It's a full integration, and it's very nice, but you need an extra electrode on the backside. You need a conductive back electrode. This was really in the 90s. People tried to do that. It has been abandoned as well, but it's a very nice revival these days, at least for, let's say, environments which are, let's say, UHV, or let's say low temperatures. Next thing, we want to look on piezoresistive, and that's a really nice thing that people are thinking of these days again to revival, specifically also for going for UHV or low temperature measurements, including also SNUM. What is a piezoresistive measurement? Well, we take the cantilever now and make two wires. We take two of them, one and second one, that are connected, but we dope the surface with a p-doping of silicon. We change the resistivity by p-doping, and hence, when a current is passing through that wire here, as you see, and we're deflecting the cantilever, either tensile or compressive, you change the resistance. So basically what you have to do in the end is just to measure the resistance change, delta R, upon deflection, which means you take a Wheatstone bridge and you balance this off and you get a certain resistance change. So that's a very nice, actually, possibility. In fact, there are tons of pros. It's fully integrated. It's electrical sensing. It's static and dynamic. It's SM and AFM mode possible. It's low temperature compatible. But there are also cons. Every piezo coefficient, whether piezoresistive, piezoelectric, is always temperature dependent. That means if you work at room temperature, or you work basically at low temperatures, the coefficients are much, much, much diverse. So you have to keep the temperature very constant. There might be crosstalk because we're measuring electrically, and hence this is not really what you want here. Also, the issue of tip integration and noise is very one. Well, yes, sure.
What is the noise, increase in noise compared to the normal deflection?
Okay, so the increasing noise is basically because you have always an active feedback loop. So that means basically you have electronics in order to measure that. In order to make this very sensitive, you say, I take an AC current. Okay, you pass an AC current, and this gives you a noise floor that goes above the 1 f. So can you show figures on that? You're larger basically than 1 f noise for this measurement. Typically about 10 dB, okay, at 1 kilohertz, okay. Factor of what, square root 2, yeah. Okay. Franz Giesebel has tried that, 1994, and they said, okay, I'll take exactly that tip for doing STM, fantastic. You see high resolution, silicon 111, 7x7, atomic resolution, and then also doing the same thing at room temperature on molybdenum disulfide, a very modern material, as you guys know, and also getting atomic resolution. This is one of the rare works, but as I said, this was 30 years back, and now there's a revival coming back. The issue is exactly that you want to integrate these things for low temperature, for instance, and UHV. So let's change page. We discussed all these electronic properties, and they're not too much paying off at the moment. And in fact, actually, this side on optical deflection sensing is much, much more appropriate. Let's go for the first one, a homodyne interferometry. All you guys know what Michelson interferometry is, right? We take a beam, we just split it up into two beams, which is a reference arm and a signal arm, and then we just add these two beams in reflection, which means we take two frequencies, the one from the reference, one from the signal, let's say from your cantilever backside, for instance, and this means we're going to add omega plus omega, or we rather do omega minus omega. So the sum of these two things goes at 0 frequency. Again, thank you for the question. We are at 0 hertz, which means we're totally in the noise level. So we're measuring at 0 hertz, which means we have the maximum noise ever, which is bad. Huh? Homodyne is nice because it can also be integrated. Here you see a version that you go with a fiber optic to the bitter end. For instance, low temperature Atocube has that. And then actually you go for the reflection on the cantilever, and you go backwards and go with your signal here. So the interference comes here from the back side, from the interface of your cantilever on the one side, and from the ending of your fiber. So you have the glass fiber, my feast. This is my cantilever, chick. And then in the end, I keep you awake, huh? Thank you, Monica. And then basically we have the two signals, one actually back reflected from my fiber and the one from the cantilever. So this is very nice. You can make fabric compatible actually measurements. You can make a robust and wavelength independent system. It's fully integrated, it's low temperature compatible. There are some cons on it. We're measuring the power rather than actually the electric field here. So that's one of the points, because you go for E times E, which is E squared, which is power. And we need a zero position. Whether I put my cantilever here or here matters, because as you know from standing waves, we get a phase shift. Can we do better? And the answer is yes, we can. Because we go heterodyne. So we do the same thing like Michelson, but now we split up the two beams, the one beam, which is the reference beam, and the signal beam, by modulating one of these beams. You see nicely, basically, that we have now two frequencies. The Bragg cell is an acousto-optical modulator, which shifts us from the zero frequency in the sum now out by the frequency we apply here, which is about 80 megahertz. So we get out of the 1/2 ref noise. But this is one of the nice things, that we can really now work zero position independent. We get an excellent signal-to-noise ratio, a very high bandwidth for dynamics, because we are already modulating, and we have, so to say, ultra-low noise. There are a couple of noise, it's dynamic only, that we can really measure, not static. And we need a megahertz modulator, which is costly. Well, I can only say that this is a very good measurement, and we do that also at low temperatures. Second last is now actually depolarization, and I want to keep this very small or short. You guys know, if you take an optical beam, it's polarized. Let's say linear polarization. Let's turn 45 degrees, and now shoot with that laser onto the cantilever. You see the cantilever here? And we do that basically by putting a so-called calcite C window in between, which splits up the beam into two orthogonal beams, one vertical and one horizontal. Let's say S and P, okay? The S goes on the back side, the P goes on the front side, which means we make a differential measurement. It's the best differential measurement ever, that you say, here on the back side and the front side, we can really measure what is the relative deflection of my cantilever. So that means what we're doing is exactly what you know from ellipsometry. We're shooting with a laser on it, and we want to know what is the signal that comes out. We don't know what the sample is, what it does to the signal, but what we're measuring is basically the turning of this polarization. We start with, let's say, spherical, let's say S and P, same magnitude, and then we get an elliptical polarization, and we turn these ellipses. These are the two values in the end that you measure on the detector. That's the same thing here. You measure this with two photodiodes, 1 and 2. Very, very, very bulky because of discrete elements, very costly, but the best resolution ever that you can really see for common mode rejection here. Now we come last but not least to the one actually that is really the one everybody's using these days, at least at room temperature. It is something that you can really do, even in vacuum. You go for beam deflection. That means we take cantilever, take a laser point on the back side, as you can see nicely here, and then we go basically bouncing off this beam left and right or top and down, which means we're measuring simply the differential image, differential, let's say, reflection by two photodiodes on it. Or you go for 4 quadrants, which also means that we can go for both in plane, lateral forces, and vertical forces. I think you're familiar with that. Most of you are familiar with that. If not, you can ask me. The nice thing about that is it's very simple, cheap, accurate, robust. So that's why also most companies have really implemented that one actually in their gadgets. Cons are really for low temperatures and for vacuum applications, because that's the issue. So let's compare that. Yes, please?
It's not working for low temperatures.
It does work for low temperatures. The question is, okay, you need a detector, possibly if you take a fiber to get out, it's fine. If you take a semiconductor, basically it's closing up. So the sensitivity, let's say, is really bad for the semiconductor at low temperatures if you cool it down. 77K is working fine. We're doing that. But if you want to go for liquid helium, it's difficult.
So basically, you can put detector in low temperatures.
That's right. Yeah. Because if you want to have a 4 quadrant, basically it's down there. I mean, you can say, okay, I'm going for macroscopic optics out of the low temperature, and they go really macroscopic. So the question was, why doesn't it not work actually at low temperatures? Yeah, okay. Good. So we see basically in this comparison table actually that we have all these 5 or these 7 systems with all pros and cons. If it comes to really sensitivity, then heterodyning is fantastic. I can only really cope for that one. If it goes for in-plane, pooh, we are really, really thin there. There's only so the beam deflection there, right? If you go for UHV-LT, you have seen actually where we go. Okay, so this is all about deflection, and you have the choice to couple this cantilever now to the measurement detection of your choice. You can say, well, I can elaborate that. This was basically the time in early AFM where everybody was trying out to do something. Today, you buy the gadget and you cannot change too much. But what I want you to take home is actually that you can take a lot of information by steering all the system. You can look on the polarization. You can really look on the noise that your laser diode has, and so on. There are many, many subtle things that you should really keep in mind. Let's turn page. We come to forces. So we have this cantilever, and we want to measure forces with this cantilever, and this guy is fantastic because it's sensitive to all type of forces. So basically, you can really tap around basically and see, are there forces somewhere or not? Well, that's very nice on the one side, but on the other side, it's sensitive to all forces, which means who's the right force? Which is the right force? Which force do I really want? We have tons of forces, as you guys see. We have, for instance, van der Waals forces. We have magnetic, electrostatic, long-range forces. We have adhesion bonding forces, so to say. You have even elastic and plastic deformation forces. Think of, you go on a membrane, or you go basically on graphene or graphite. You're compressing the system completely by applying a force of 1 nanonewton. So, is this all true, what I'm seeing? Can I believe what I'm seeing? So this is the holy grail, that we are able to discriminate between these forces by using the different measurement techniques I was just telling you. So, in fact, what we can come up is say, okay, we can take the tip, and we can basically say, okay, this tip is the one that we need to really have a look on. Where is exactly the coupling to every of my forces I want to see? We can say starting really at the front end, because we always believe that's the front end that does the job. Well, this is not really true, because we have tons of forces, like, for instance, electrostatic forces, but the front end might be, in fact, relevant, but possibly it's much more like a dipole or a quadrupole sitting somewhere here that is really doing the job. So the front-end nanotip, as I'm calling it, is only relevant, for instance, if we start really thinking about chemical forces. So really covalent binding, if you want to go for measuring local density of states, right? There are more long-range forces. Even the van der Waals force doesn't care too much about what is really the front end, because it's a more integral, as we will see in a second, actually, force. And also, if you go for optically induced forces, we know, and there will be a couple of talks coming then, where we induce a dipole or even a higher order mode into the tip, and this dipole then couples to my sample. So we need to really respect that. So what I want to really get you home here is that the different origins of these kind of forces is not the one and the same always. That means by comparison of different modes, we have to really think hard what I'm doing. I'm comparing a chemical bond at the front nano end with an induced dipole force at this position of my radius here, of my tip. So this is something to keep in mind when you interpret your data. Let's continue. And if you take all these forces, we can simply state that we start now by simply approaching this tip certain distances, closer, 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 and look with snapshots what is going on really. So we start above 10 nanometers. Let's go far away. So my tip is far away, okay? Much ways above my surface. And, well, that far away, we have very weak van der Waals forces. So there's a small attractive force. And if we say, okay, we can even include some bias voltage, we apply a voltage to my cantilever, then what could possibly happen is naturally that we can even have, at certain voltages, at certain fields, so-called electron emission. I'm far away. You apply a voltage above the work function, which means you get an emission of electrons. So imagine you have a 10 kilovolt, or let's say even 10 volt on your cantilever. The tip shall be conductive for this, and you apply a voltage, you're far away, bang, you get electrons out. Okay, possibly they don't arrive on your sample because you are working in air, so you get dissipation, you get possibly even sparking. But nevertheless, this is something you have to keep in mind. It's called the Fowler-Nord time tunneling because it's a field emission current, right? Now, even if you don't apply a bias voltage, my tip here, metallic, my sample, silicon, are two different materials, which means we inherently have a certain bias voltage because chemically they're not the same. So we have a chemical potential difference, and Rainer was already saying about Kelvin that comes up basically on Thursday, and we will see then actually what is exactly this giving us. So let's go and now approach. We go smaller with the distance, Steve. We go smaller between 1 and 10 nanometers. We come down, okay? What happens? At these intermediate, we have still long-range interactions. We have van der Waals, but no tunneling. So that means even the electrons, they stay actually where they should be. And we get actually already some kind of wave function has been modified. On the atomic scale, the density of states that we are really taking as an integral for measuring the interaction is already modified. If you go closer, clearly we get, so to say, a tunneling current. This is exactly where STM then is really relevant, 0.3 to 1 nanometer. We get strong attractive forces, and there's an electron transfer. Now, if you go closer, we go even to 0.3, which is quite the diameter of, let's say, one atom. We get strong repulsive forces, polarly, and the atoms might even touch. Now, what you do when you take an AFM, for instance, in most cases, and you go, for instance, for this famous, let me call it tapping mode, is you go basic and you go into it and you go out of it again, you go into it and you go out of it per cycle. Which means, imagine what happens. You start up here and you go into it, and you go back out of it, and you go into it and out of it. So you see, many things happen at the same time, and you're not aware of, possibly. Electrons can really change positions. They can basically transfer from tip to sample, simply because we have different biases, we have different electrochemical potentials. And hence, everything of that can really happen here. On the other side, you can even have emissions of electrons down here. Then we're going through a whole zoo of forces. So it's not as easy as we think in the beginning. So let's see how we can really cut this down into something doable. And we start basically with the most famous forces, which are also branded in the so-called Lennard-Jones potential. We just take one attractive, shorter range force, which is the van der Waals, and we take the repulsive force, which is the Pauli repulsion principle. And this is all again brought together by Lennard-Jones here, that you see him here. So let's start with the greenish one, which is the van der Waals attractive forces. Van der Waals generally is thought of as an attractive 1 over potential 6 force, but there are 3 contributions. Be aware of that. There are 3 contributions which have 3 names: Keystone, Dubai, and London. What are they? You see nicely here we have dipoles. These are dipoles. Imagine we have 2 dipoles talking to each other. They can orient, and basically one makes a field, electric field, the other one is actually orienting in this field, coupling to this kind of field, and hence giving us an orientational factor Z orient, which goes 1 over power R6. Dubai says, well, we take a dipole, but we take the second partner to be not being polarized yet. So it's an atom, for instance, and we know atoms have electrons, they have ions, and we have a core, which means this field of my dipole here is producing an electric field at the position of my second atom, which is inducing a polarization called polarizability. That's exactly what alpha is, the polarizability. We are polarizing, inducing a dipole. It's an induced dipole. That's why the factor is called induced dipolars. The third and last one is basically this kind of where we have 2 polarizabilities, alpha 1, alpha 2. Nothing is a dipole yet. And due to random fields, electrons made pivot and so on, this kind of randomized actually field on the alpha 1 is producing a field at position alpha 2. This one is talking back to alpha 1, and hence we get 2 induced dipoles talking to each other. Again, if you just omit retardation, it's a 1 over power 6 law. And if you put this all together, as you see, we end up exactly in the total van der Waals. The force, so to say, naturally is a derivative of this one, and to give you some numbers, The van der Waals force typically that we are looking at in AFM or scanning force is typically on the order of 1 nanonewton. And this means that the distance then for that 1 nanonewton is already on the order of about 0.25. Now, it's 2.5 angstrom, it's 0.25 nanometers. If you go further away, if you go 1 nanometer apart, that force goes down to below 0.1 milli-electron volt, so very low. It's a very steep, so to say, attractive interaction. The second very important force that we are looking at are the repulsive forces. And you see nicely there are different models being proposed for the repulsive forces. On the one side, hard sphere. You take two spheres until they touch. And once they touch, the repelling force goes up infinitely. That means my n goes up to infinity. You see it's a potential law that has really a straight value. We can take a power law where the n is not infinite, but something between 9 and 16. And in fact, Lennon Jones said, okay, let's take 12, because it's just in the middle. That's why we all talk about the 612 potential, right? But it can be anything in between there. Then the exponential law is the final one that is also describing the repulsive forces. This is very nice for everybody who does computer calculations, because the derivative of an exponential is an exponential, and hence basically it's the best that you can really use there, right? So, long story short, we take the Pauli force, which is exactly 1 over power 12, and if you put these two things now together, as you see nicely, we have the attractive contribution, which is the right thing here on the 1 over power R6, negative, as you see, that's attractive, and we have the repelling force, the bluish one, which is exactly the Pauli. In total, we get, so to say, exactly this kind of curve with a minimum at a certain point right here. Well, one thing is very important at this point. What we did so far is exactly we take a point of my tip, the front end, really the front end atom, and I take 1 atom in my sample. 1 atom, okay? So it's a pair potential. That's what we did. It's pair, nothing else. It's not a sample that is extended with many atoms. It's not a tip which has many atoms as I have here. So we have to respect for that. Well, the other forces that we will really talk also later, which means on Thursday, electrostatic forces come in at energies, as you see, 100 to 4 electron volts, really large energies. We cannot forget about those ones, because they matter in our small interactions. They're magnetic interactions also from 10 milli-electron volts up to 1 electron volt. If you want to measure scale muons or so, then you have to respect that. Or if you go now for induced optical dipoles, like we do in SNOM, then actually our energies go from 0.1 to about 2 eV. So you see again, actually, in the energy scape, actually what that means. We have tons of energies that we are adding up, and possibly we're not knowing what we're doing. So I just said we have pair potentials, 1 atom here, 1 atom here in the sample. Now, we do see that this is a finite distribution of my tip. It is a finite distribution of my sample. How do we cope with that? So we need 2 corrections to do. You see the 2 corrections called in the Lifshitz theory, and you can really read it up also in the Jacobs Israeli's book, which is very nice on that. Let's start simple and take the 2 things separate, the sample and the tip. If I take a sample, let's say that's my sample here. I take a tip atom, my feast. I need to do this integral of pair potentials over all atoms that I have in my sample, which means that my tip, so to say, goes not only to this surface point, but every point in my sample, including subsurface interactions, for instance. So you make an integral laterally and into the depths, and you end up with something that is reducing your power law. Second point, my tip. The same thing, my sample is extended, my tip is extended. I have to now integrate also over my tip, because it's not a single point in my center. We always think about the dipole possibly sitting in the center, fine. But nevertheless, if you take really my real tip, and it's a real tip here, then you see nicely we have to integrate over all tip atoms. So this is the big question. How relevant is this distribution? And they come back to the different forces that we had. We have different relevance radii for different, let's say, interaction lengths. If you go for an atomic length covalent interaction, it's just the front-end atom. We finish by a pair potential. If you go for a dipole, then you have to really integrate over the whole system. This means, in the end, that our fantastic 6-12 potential that we just had from the pair potential ends up in a 1-7. So we're losing 5 orders of magnitude in the van der Waals. We're losing 5 orders of magnitude in the repulsive. So that means my Lennard-Jones potential is not as steep as I think. It's ways less steep. And you're going to basically approach a cantilever exactly into this very soft potential now. Huh? It's not as steep as you think. This is the first correction, the finite size of tip and sample. Second point, there's an environmental impact. Most of you work, for instance, in air or so, or in vacuum. That's fine, because then my medium has a dielectric constant of exactly 1. Now, if you compare that to the dielectric constant of my tip, let's take silicon. Question to you guys, what is the epsilon of silicon? 12. So 4, okay? More?
11.7 around in mid.
Exactly. So how does it go together from 4 to 16? Huh? So 4 is the refractive index. So it's basically between 3.5 and 4. And if you go, basically, you have to do n squared for epsilon, which means we go something between 12 or 11.7 and 16. So let's take 10, because we can calculate easier with 10. Okay. Okay. So if I take 10 for my tip and I take a medium of 1, which is basically my medium, which is air, we get, so to say, for my van der Waals attractive force, U, 10 minus 1 is 9, 10 plus 1 is 11. So we get, so to say, yeah, roughly 1. Okay. Now let's go for water. We go to the same experiment. We want to do SNOM in water. We take an AFM, we put it under water. We go for a medium that is 80. Water, dielectric constant, DC, is 80. I go from 10 minus 80, which is minus 70. I go 10 plus 80, which is 90. 2 things, you see, I'm changing sign. My van der Waals, who is attractive, becomes repulsive. Interesting, huh? So in water, basically, and changing the medium means you can basically change the effective sign of your van der Waals. The other thing is the weighting. How strong does it impact actually on it? And you see, it's really a matter. So these 2 things, keep them in mind. They have to do exactly the way you operate the medium and the size of your system. So Jacob Israeli was really doing that, and he said, okay, let's go from pair potential developing into, so to say, 1 tip, so to say, in front of a surface, and then go from this one to a finite size. And he was even developing an instrumentation called the surface force apparatus, because he found out that this tip, roundish tip, spherical in front of a flat surface, is exactly the same thing like 2 cross cylinders. So if you take 2 cylinders, you cross them, you get exactly the same topology of the system. It's also 1 over d for van der Waals, 1 over d for van der Waals. And that's why he was using 2 mica sheets, bend them a little bit, coat them, and measure the interaction in his surface force apparatus under liquids. So this goes together, and this was in the 70s already. So much, much earlier than actually STM. Okay, now let's go for SFM operation modes. We need to now really work with this kind of potential, and we start really simple. I'm going back to the 6-12 potential because you can develop it much easier. So the first thing we have is really the potential, as you nicely see. We have, again, this potential curve, 6-12. Now we want to measure forces, and that means, in the end, we need to take the derivative. So this really minimum in the potential gives us the 0 crossover at this point in the force, and hence the deflection turning point at this point gives us the minimum in the force. We go from the force here to my force derivative, because we want to make also gradients later, and I do the same thing. I take this point, so to say, the minimum goes to my deflection point, my 0 crossover here, and this one here. Why do I doing this here? Well, okay. What you see here with this bottom curve, since this is the interaction potential, is exactly that we see with this curve here, this is the spring constant of my interaction. We know this cantilever has a spring constant K, right? Now, what about my interaction? I want to interact with my tip to my surface, my measurement I want to do. And we see nicely that this is not a constant spring constant. A negative force, so to say, minus F prime, is something, derivative f divided by df over dz, which is a spring constant. This is the spring constant of my interaction, KTS, tip sample. And you see nicely that spring constant sometimes is negative, and that spring constant sometimes is positive. And we're coupling with my spring here to that spring of my interaction. So we're making two springs interaction. That's exactly what the force is about. So let's see how we can really do that. And for that, we need the full potential. We have, again, the 612 potential as we see here. And we take, so to say, the potential of this cantilever, which is, again, as you see, the harmonic potential. So we have a deflection out of Z0 here. This is my harmonic potential. We have to couple that to actually this one here. And we take this as a normalized version. ZA is a distance at which the potential is 0. So you see, basically, this one is ZA, which means exactly here. My potential crosses 0, bang, at this point. Let's take this as a norm, ZA. And so what we do now is the following. I take a sample. I take my cantilever, and I'm looking at different distances. What kind of interactions in my potential curve do we see? So let's start. We take again this formula, and we start basically in the first picture at a distance far away, 4 times CA, so far away. So you can imagine, this tip now feels an attractive force. Maybe it's bent a little bit, okay? But in fact, if we solve this equation here, we get a saddle point, we get a minimum here at this point, close to the 4, which is a stable point. If we go closer to Z, 3 times ZO, we go here, a little bit more shifted below the 3, but still something which is in the potential, the minimum here. But you nicely see that this saddle point here comes down already, the point E and G. And if you continue with this, you see basically we go to 2.3, we suddenly drop into a minimum here, which goes below 0. Although my cantilever stands at 2.3, which is here, it feels an attractive force and says, bang, I want to snap in. It goes directly to the surface. You can't prevent that. It goes to the surface. That's exactly the snap into contact. Although the tip stands here, it goes exactly at this point, 1.4. And if you go for 1.5, it's even more dramatic. It's down here. So you see actually what happens is that the attraction of this cantilever due to the different force constants, KTS and K, makes my cantilever snap into the surface. You can really imagine this. These are the 4 plots at the same way. Imagine you take a small bead or a small ball and you just roll that down. You put it in here at the ball and you just wait until it's rolling down into the minimum. You will find it actually in the end here, right? That's the minimal position. Do the same thing here. Maybe it might stay here. It's a quasi-equilibrium position. We don't know. And here it will definitely roll bang into the minimum. So that's exactly what happens. The system automatically finds the minimum by really wanting to go into this snap-in position. This is not good. And the question is, can we prevent that? Well, let's do the math first. Let's go for the math solution of this equation again. We have this full potential, and we want to look on the minimum of this potential, which means we have to put the 0, which means that this tip-sample interaction has to balance off with the force that we have here. And in fact, the tip-sample force is balanced by the cantilever force. Finished. At the same time, and that's now the important thing, is we need also a certain deflection, which means the second derivative needs to be positive, which ends up that my force constant of my cantilever here, this K, needs to be larger than the force constant of my tip-sample interaction. That's exactly the KTS. If I want to prevent the system to snap in, I need a force constant, K, that is way larger than my tip-sample interaction. Well, in the beginning, we don't know the tip-sample interaction, right? You never measure that, possibly. So here is actually the whole snap-in process in a nutshell. We start basically here, and you see that's not the potential, but that's the force now. We see basically the tip-sample force in reddish. I take my cantilever spring constant, as you see. This is force, this is distance. The greenish one is the force constant K of my cantilever. And so if I'm going to approach now my cantilever here, as you see, I can do that. We're coming in basically, and it feels the force, and then bang, it goes right into this minimum. And the reason is that my force constant that we have here, as you nicely see, we can do that mathematically or geometrically approaching the point C, and hence we get from C to D. So take 2 points which are connected. That means basically the system does not know whether to stay at point C or D because they're on let's say, force. And in the end, this one is the lower one because it's a lower force, so it snaps into D. On the way back, if you're in here, the same procedure. We want to go back, so we go backwards. We are down here. I'm pulling back. My tip stands until I'm here, and then bang, it snaps down here, up here to the A point. So you can take the K value. You plot this force, actually, as you have it here. Oh, sorry, wrong. You plot this force as you have it here, and you go and basically draw this. So you get basically a hysteresis between A to C to D to F to A. This is an energy because it's force times distance, right? This is energy, this is dissipation, this is adhesion energy. So at every cycle when you go down with your tip snaps in, and then you're pulling back because we, for instance, go for a tapping or so, and hence you have a dissipation of energy at any of these oscillations. And you can see how much that is. It's just a hatched area between A, C, D. So you can hatch that, and you see quantitatively how much energy is gone. This means now we can really differentiate between the different, let's say, modes. On the one side, we can say, well, contact is then exactly when we are left of this snapping point. We want to just go only into the repulsive regime. Huh? We are then really working the repulsive regime. If you want to go really on the other side of the snap-in, we go attractive only. And if you go over that point of snap-in, it's exactly what we do with tapping or intermittent contact. You name it, there are different names on that. So you see, actually, we have to really look on the force constants with relation to the tip-sample interaction there. So put this into figures means that we have now the repulsive interaction on this side. As you see, we have forces which are really strong, and we mostly go for static measurements. That means the deflection is really statically. My bending is exactly this way. We have a large adhesion, a large contact area. We can use one of the deflection methods that we just were discussing before, and in order to measure that and scan. If I go basically for attractive, I want to stay at this rim. I never want to really go basically beyond this point, which means I need a force constant, dF over dc, which is large enough in order to avoid that snap-in. And hence, I can then basically take a mimic to really dynamically mostly really measure that. We do that dynamically simply because if you go statically, as I was just really shown before. Okay, now maybe. So you basically see, actually, if I go dynamically, I have a much larger sensitivity for doing so. So this is the way we can really differentiate between these different modes. Now, I would like to break the ice really for the actually dynamic modes. We need for that an AC to DC conversion, right? Means I'm exciting my cantilever, as we have it here. And hence, I have to really measure the deflection. And I want to really use something like a lock-in amplifier or something which is really giving me a conversion from the AC signal into a DC signal in order to really feed that back actually into my system. I don't know whether you guys are really familiar with what a lock-in is doing. Just a quick sketch here, which I borrowed here from Zurich lock-in, Zurich instrument. You just take a signal in and you compare, so to say, with a certain reference signal. And then you say, okay, I'm going to do that once at 0 degree, and I'm going to do it once at 90 degrees. You guys are familiar with transformers, 50 hertz, for instance, in the power lines. You take basically, and you want to make a DC out of that, which means you always go this way. This is a very important thing, this kind of mixing, because you get two signals out, and you can do that now for my amplitude of oscillation. You can do it for the phase of my oscillation, but you can also do it for the frequency. And this is the holy grail, how actually you to operate your system. Most people take that phase. And now this phase contains any kind of force interaction, the mechanical phase, the optical phase, everything that is acting on my cantilever. I can't really say. And that's really the point where you have now to think of how can we differentiate? Because the goal is now to take this non-contact mode, shake it here, take any kind of deflection, the backside, and then say from that oscillation, can I take that as a frequency shift. I'm looking on delta F, the frequency shift, and just use that as topography. Well, at the same time, when we do this, as you guys know, we already said, I'm going to oscillate that, and there's a certain damping, right? So we're having a losses in the amplitude. Now we could also say, okay, why not to take this oscillation amplitude and keep this constant? If I'm keeping this oscillation amplitude constant, I have to feed in here on the back side with a certain feedback loop that my drive is always the same. I can use this as a signal in order to measure directly the dissipation, SDM, dissipated power. I can really have a feeling on that. I can also, at the same time, use the same lock-in, or let's say the same signal, in order to go for Kelvin, and so on. In the end, and that's exactly what we want to discuss actually then on Thursday, we will use about 3, 4, 5 different feedback loops in order to disentangle whatever you have in here in order to make different modes of measurement. You get topography, you get dissipation, you get signals like the electrostatic, you get capacitance, and so on. And furthermore, if you have your illumination with SNOM, then you need another lock-in, and also there is a phase. But you should be aware of that, not to really mix this up. Well, what I would like to do for the end of this lecture is now the following. In order to really make this kind of thing happening, I have brought an experiment here, and I would like to invite you basically to do that after the lecture here in front, because I cannot show this really too much. What this is actually nothing else than an oscillating cantilever. You see, basically, it's a small cantilever, and I have basically here a sample, and you see 1, 2, 3, 4, 5, 6. And what I want to show you, and I will do that basically for the people in the camera, not for you, is actually that you see actually this tip is oscillating, and there's an attractive force, which is increasing, now which is decreasing the frequency. And if I go basically for a repulsive force, we're going to have basically a higher frequency. We're looking on frequency mode, FM, and you can really play with that. Hopefully you saw that. You can play down with that. I'm going to put it right here. Don't break the tip. Okay. Why is this dissipation important? Why do we need to disentangle this? And the reason is because of the physics. This is nothing else than my harmonic oscillator that we have here, right? Now we have dissipation, which means my gamma 0 is non-zero. That's the point. Otherwise, this would be really out. We solve, we can go home, finished. This is basically my oscillation here, and this is the drive. My hand is driving it, and we do have a couple of interactions, like tip sample. Now, to solve this kind of differential equation means we need to do the following. We need to really apply, again, the same formalism as shown before, cosine, sine wave, sinus hyperbolicus, cosine hyperbolicus. Most people, if you do that, and you did that in school, you solve basically one of the equations. You say, I'm going for that solution, which means I'm using cosine solution, because this is what we call in physics the so-called conservative forces. We're not looking on the imaginary part. The solution contains cosine plus I sine, right? There's a complex number as well, because this is a complex sim. If you take cosine, make derivative, you get sine. So there are two equations that you have to solve. The first one, which is the conservative forces, and the second one, this is at the damping, as you see. These are the losses, which is the dissipation for the sine waves. Most people forget about that, and I would like to break the ice that you can do that in a very, very concise way. You can go down to measure dissipations down to 1 attowatt, which means your tip, so to say, on one cycle dissipates 10 to minus 18 watts, which is very small. And I've done this basically for now 100, let's say, 1,000 Q values, and that's 100,000 kilohertz for 100 kilohertz, sorry. Now, if you go for room temperature where your Q is lower, and your resonance might be different, and your oscillation might be larger, you plug in different values, and you end up with dissipation on the order of about 1 to 10 nanowatts per cycle. So imagine that's exactly the energy that goes into your sample, or in your tip, or whatever you name it. So you see, in the end, this is very important that we know what we are doing by this kind of oscillation, because we're hitting the surface, we are coupling to the sample, and to make it even more complicated, these are all the sources for this kind of dissipation. And you see, you can write up tons of projects on that if you want to. It's not solved because very, very few people are really working on that. I like to finish this lecture now with the following take-home messages. First of all, the geometry is really the important thing that determines my K of my cantilever. We saw actually that the higher order resonances are very important, and we can solve them by going for the equation of motion. Then it's very important that you select the deflection measurement tool of your choice that does A, the bandwidths, B, the sensitivity, and C, the appropriateness for your measurement, like say a low temperature or vacuum. Now, be aware of this here. Our tip is really stupid because it measures all forces, unless you say, okay, I want to be really measuring one type of forces only. And you can choose between that by using different operation modes, the distance at which you operate it, the amplitude at which you operate it. So the operator allows to discriminate between those. And be aware of that when you interpret your data, that we don't have a point-to-point interaction. I don't know how many people really know that, but it's really an assumption to take the Leonard-Jones only. But in reality, it's much more complicated. There is snap-in. Beware of that. And you have, hopefully I showed you how to really do this without that. And last but not least, dissipation matters. And with this, thank you very much.